Okay, so we're going to talk about ticker tape velocities. Do you guys know what a ticker tape is?
No.
Those of you that have been fortunate enough to have Mr. Reason for grade 10 science.
But then he decides that I'm not going to leave the room and he's going to do a ticker tape lab when I'm writing a test in his classroom. He's not letting me leave the class. I'm very annoying.
Okay, here's the ticker tape. Okay, and what it does is it's an old school sort of, you remember the graph thingy I had with the motion sensor and we got the graphs on the screen and stuff? It's the same idea. Okay, it just doesn't do it by computer, right? So what they had was they had a little device like this. You'd have like a cart and you attach the ticker tape to it, and there's a little thing on the end, and it would just spin around at a constant speed and would put a mark using carbon paper on the tape. And if the tape was moving at a constant velocity, well then the marks would be same distance apart. And if the tape was accelerating, that was just going, didn't you? Then the little marks would get what? Farther apart. Kind of like that cannonball thing that you're working on right now. Hint, hint, hint. Okay? Do you guys know what a ticker tape parade is?
Parade?
Yes.
A whole bunch of ticker tapes lining up and marching to
Good guess. No. A ticker tape parade, the stock exchange in New York used to run on ticker tapes. Now, you know, they got the ticker, you know the ticker on the bottom, TSN?
Yeah.
The score ticker? Ticker tape, same idea. Okay? The stock ticker, if you ever watch the news channels, they have that as well. In the old days, on the stock exchange, they would print out the value of the stocks on a little strip of paper like this, right? And then the broker would look at it, and then as it would change, then something new would come out. And they would have, at the end of the day, they would have tons and tons and tons and tons and tons of little strips of paper. And then when the Yankees won the World Series, they would have a big parade, and they would throw all the paper out the window.
Would they actually?
Yes, they would. Hence the name Ticker Tape Parade. They no longer do that, and not because the Yankees don't win the World Series anymore. It's because now everything's done by computer, and it would hurt if the Yankees were hit with computers flying out of windows. So now what they do is they take a colored piece of paper and they cut it up, and see, at least in the old days it was recycled paper. Now it's just colored strips of paper. There you go. That's the origin of a ticker tape parade. Okay? Having said all that, let's move on. Okay. Now, you've got this sheet. All you have to do is do the drawings. Okay? So you need to put away the hand-in assignments that you had time to work on Friday. And you need to draw these in this handout that I've just given you. Okay. So, we are talking about, did you see that thing move? I'm just going to go back here. Constant positive velocity. Watch it move. It's moving at a constant velocity. When I say constant positive, that means it's moving to the right. I'm not going to bother reading that. Okay, you can read it on your own if you want. But it creates a ticker tape where the dots are the same distance apart. The ticker tape has the dots the same distance apart. So what you draw is you draw a little ticker tape and draw the dots the same distance apart. Do just like this. Okay, do just like that. And then underneath that, I want you to draw the following graphs. Okay? You'll notice that the position time graph is a straight line. See how it's a straight line? Why is the position time graph a straight line? It's moving at a constant speed. The velocity time graph is flat. Why is it flat? Velocity stays the same. It's moving at a constant speed. The velocity stays the same. In fact, it's a value of about 12 here.
Do we have to put the value? Or
no, the value doesn't really matter. Just the shape is what's important. The acceleration time graph, what is it?
0.
It's flat and it's at 0. How come it's flat and it's 0? It's the slope of this guy, isn't it, right? The slope of the velocity time graph is the acceleration. The slope of this is 0. So moving on, you'll see the next one is constant negative velocity. Let's do a little bit of a prediction here. Ladies, you should really put the hand in away, because then you're not going to get this stuff. You've got to focus your mind on this stuff, okay? If I get through all this, I'll give you time to work. Constant negative velocity, what's the little dot going to look like? Are the constant negative velocity, the next one, are the dots going to be equally spaced?
Yes.
How come? Constant. What does the negative mean? Just going the other way. What are the graphs going to look like?
The same, just the opposite.
The same, just the opposite. I don't know if Sesame Street would accept that.
The same.
Constant negative velocity. There's the dots moving left, equally spaced. You'll notice that the position time graph is sloped down because it's a negative velocity. You'll notice that it's also below zero because this is my 0 point over here. You'll notice that the velocity time graph is flat because this has a constant slope. And once again, the acceleration is zero. How come? Because the velocity doesn't change. Making a bit of a prediction. Flip the page over. The next one says positive velocity, positive acceleration. So positive velocity means I'm moving to the right. Positive acceleration means my acceleration is also to the right. So what should it be doing?
Getting farther apart.
Speeding up, and the dots do what? Getting farther apart. The dots get farther apart, and they're going to be moving to the right. What are the graphs going to look like? Positive velocity, positive acceleration. There's that little blue dot, speeding up to the right. Dots getting further and further apart. Position time graph is curved because it's speeding up, which means my velocity time graph has to be increasing because my slope is increasing. Velocity time graph has to be increasing. And now because I do have an acceleration, I have an acceleration time graph. It's still flat, but it has a value. In fact, its value is the slope of the velocity time graph. Okay, so once again, a bit of prediction here. The next one is positive velocity, negative acceleration. Positive velocity means moving to the, Sonia? Positive velocity means moving to the, negative acceleration though means this way, so it's going to be slowing down. So what are the dots going to look like? Getting closer together. And now I'm asking you to think about what are the graphs going to look like? What's that position time graph going to look like? If it's slowing down. Slowing down means the slope has to be doing what?
Other way, curving down.
Is it going to be curved? It's going to be curved. You think it's curved down, Sean?
Yes.
Positive velocity, negative acceleration. Dots getting closer together. It's curved up but flattening off.
That's what I meant.
Why is it curved up? Or why is it going up? Because it's moving to the right. It's moving to the right. Why is it flattening? Because it's slowing down. It's flattening because it's slowing down. Right? When the slope gets flatter, it slows down. And the velocity time graph, it starts up here at 20. It has a speed, right? And then it slows down, which means the velocity has to be approaching zero. In fact, when it gets to zero, it stops. So it's down towards zero. Down towards zero. And the acceleration time graph, I'm going to find the slope of this. It's a constant slope, and so it's going to be negative. In this case here, about negative 1.5 or so. Yeah.
What would the acceleration graph look like if it's sped up, then slowed down, then sped up again?
It would be flat, negative, and then it would go up to positive, and then it would be like a...
Would it just go straight up?
It could, yeah. I mean, it would probably have a little bit of an angle to it, but yeah. More than likely it would be straight up, yeah. Okay, so the next one is negative velocity, positive acceleration. Negative velocity means it's moving to the left, but positive velocity means it's backwards this way, and when the signs are opposite, that means it's going to be, I'm going this way, and my acceleration is back this way, slowing down, right? Negative velocity, though, means that it's going to be going to the left. Now, what do you think those graphs are going to look like? Slowing down means that the slope of the position time graph has to be getting flat. Let's see here. Oh, is this the one? This is not the one, is it? This is the one that I always miss, and I always say, I got to fix that, and I never ever do. So here's what you need to do. I tricked you. On the back page here, you need to write, go to the back where it's blank, because I missed this one. Negative velocity, negative acceleration. My apologies. Every year I say I'm going to fix it, and I never do.
Fix it.
I know, maybe this will do. Negative velocity, negative acceleration. That's all you need to write. Don't worry about writing all that other stuff. Negative velocity, negative acceleration. Negative velocity means it's moving to the left. Negative acceleration means that it's going to be speeding up to the left. Moving to the left and speeding up. Dots get farther apart because it's speeding up. Now look carefully here at this position time graph. It's speeding up, which means the slope has to get steeper, but it's going left, right? So it has to be in the negative territory. So that's why it's down below like this. Okay, that's why it's down below like this. Velocity time graph, it's getting steeper, and so my graph is down and negative. The value of the slope is getting steeper. The value of the slope is getting more and more negative. So the graph here becomes more and more negative. And the acceleration, because this is a straight line, the acceleration is, it's negative and it's flat. Okay? A little bit tricky.
So it's the same, but like flipped over the
Yeah,
x-axis.
pretty much, yeah. What do they call that in math when it's flipped over like that? Reflected, right?
Yeah. I was trying to figure that.
Yeah. Reflected. Good. Okay, now you can go back. Now you can go back to where we were there. Negative velocity, positive acceleration. Negative velocity means it's going to be moving to the left, but positive acceleration means it's going to be this way, so it's going to be slowing down, right? Negative velocity, positive acceleration, moving left, slowing down. Because it's slowing down, that position time graph has to flatten out. Has to flatten out. Here the slope becomes less and less and less and less and less. And so my graph of my slope starts very negative. The slope here is very negative, and it gets closer and closer and closer to zero. Because it's a straight line and it's sloped upward, that makes my acceleration positive and flat. This one here, you're going to have a little trouble drawing. I would recommend you just draw the graph at the bottom. But let's just talk about it first before you start drawing. I will give you time to draw. Put your pencils down. Okay, we got two cars here, the blue one and the red one. Okay, now you'll notice, would you say that they're both traveling at a constant velocity? Kind of hard to tell because it's kind of jerky, right? But they are indeed traveling at a constant velocity. Which one's traveling faster? The red one. Can you tell me at what time in seconds does the red car pass the blue car? At what time? 7 seconds, right there, right? 7 seconds. We're going to assume that's time. It must be. Right there, they pass. Right? Can you tell me at what position they actually pass each other? 60? How would you do it if I just gave you the graph? How would you find out what point they actually cross each other just from the graph? And I'm going to have to stop the animation here for a second.
I go where they cross, and then go.
How would you do it, Nick?
Find the second point where they cross, and you go up and over and find the position point where they cross.
There's the blue one. Oh. Was it 3 seconds? I think it was.
4.
We started at 4?
Yeah.
Okay. Okay, so it looks like that, right? How could you figure out the position that they cross? How do you get... We know the time, right?
Yeah.
It would just be right there, right? You just look and see. They would cross at 7 seconds, and they'd both be at 60. How could I tell how fast they're going? How do I tell how fast they're going based on just the graph? Find the slope. Find the slope of the blue line, find the slope of the red line. Which one's traveling faster? The red one. It's steeper. Okay, draw that. Draw that picture. Label the important points. Label the 4 and the 7 and the 60 and so on. Label the important points. I want you to draw the corresponding velocity time graph for those. Show me what the velocity time graph would look like for these cars. Okay? If you make a mistake, that's fine. You can put like a guess, and then we can put the actual. We can put on the back if you want, but I want you to make an actual guess. Tell me what you think the velocity time graph is going to look like. Here's the answer.
No. Yes. What's up? No.
Many of you had a graph that was very similar to this, except you had both the graphs starting there. The red car doesn't actually start, you don't see it until 4 seconds has elapsed, right? So in fact, the graph actually starts there. Now if you had that, I would probably give it to you, right? Because I mean, the car would have to be moving that fast before you just don't see it, right? You could certainly argue that would be right. That's good. If you guys got that, you're good, okay? You would find the slope of the blue, you would find the slope of the red, and then you would graph it. Now, one last question. Can you tell me from this graph, when do they meet each other? When are they at the same time? How would you do it? How do I find out when they meet each other, cross each other?
Look at the first round.
Good answer, I guess. You know it's possible, don't you, Ben, right? You just have a feeling it's possible? Alex?
Well, the velocity, you just have to calculate the velocity. I don't know how to explain it.
How do we find position from a velocity time graph?
You switch the thing when you're trying to find velocity.
What's the process for finding displacement from a velocity time graph? We've been doing it. Hey? No, I want to find the displacement. That's the velocity, right? I want to know the displacement from a velocity time graph. How do we find it? We've been doing it. How do you find displacement from a velocity time graph? You do the coloring. You find the what? Area. So you would have to actually, and Alex was right, Connor, you would have to actually take a guess, right? Like maybe 6 seconds. You would have to find the area up to 6 seconds, right? Find the area here up to 6 seconds and see if they match. And if they don't match, well then you have to go farther, right? And you'd have to go sort of bits and pieces like that. I guess the alternative would be to learn calculus, and you could do that too.
Yeah, I don't get that.
Okay? You have to find the spot where the areas match, because they are equal displacements. Okay, that's good. All right, I'm going to stop talking. I'm going to give you time to finish up all these things that you guys need to be working on. Tomorrow I'm starting the last little topic, which is word problems. You need a calculator, you need a sharp pencil, and your brain needs to be ready to go.